Hello everyone. In today's class, we will discuss one most important topic, that is relations in discrete mathematics. So this is a very important topic in unit number 2, set theory. Here we discuss definitions, properties, and how do we represent relation in matrix form and diagram form, and also we discuss types of relations and equivalence relations, right? Let us go to our topic. So first of all, what is the definition of relation? Relation is nothing but relation is defined as an ordered pair. An ordered pair defines a binary relation or a relation. Okay, generally we define a relation is an ordered pair. It is also called binary relation, but simply a relation. But a relation from a set A to set B. A relation from a set A to set B. Relation from set A to set B is defined as subset of the Cartesian product of A cross B. Relation R from set A to set B is nothing but subset of Cartesian product of A cross B, right? Okay. Now that means it specifies how elements of A are related to the elements of B. Okay. So the subset of the Cartesian product is defined as relation from A to B. It specifies how elements of A are related to element of B, and what rule elements of A are related to elements of B. Say for example, if we take A is equals to 1 comma 2 comma 3 and B is equals to A comma B, then we write a relation from A to B as 1 comma A, 2 comma B, 3 comma A. Okay, it is a relation from set A to set B. All we know that Cartesian product is nothing but all combinations of ordered pairs from set A to set B is defined as the Cartesian product. So that clearly it represents, clearly it is a subset of all combinations of the Cartesian product A cross B. So it is clearly a relation, right? Now we move to the next one. Domain and range of a relation. Domain and range of a relation. Domain is nothing but the set of all first elements. Set of all first elements in the relation. Range is nothing but the set of all second elements. Set of all second elements. Second elements is nothing but range. Say for example, if we take R as 1 comma A, 2 comma B, 3 comma A, then what are the first elements? 1 is the first element, 2 is the first element, 3 is the first element in the relation. Therefore 1, 2, 3 is the domain. What are the second elements? A, B, A. These are the second elements. Therefore A comma B is the range of this relation. Clear? Right. Now we can represent a relation in matrix form. So to represent a relation in matrix form, we need to take first elements as rows. First elements as rows. What are the first elements here? 1, 2, 3. And second elements as columns. Second elements as columns. That means first set elements are, we have to take as rows, and second set elements we need to take as columns. Now we need to observe, is there any relation between the rows and columns? That means from 1 to this element, is there it is existed in relation or not, we need to check. If it is exist, we need to keep it as 1, and if does not exist, we need to keep it as 0. So 1 to A is exist in the given relation, so we kept 1. And 1 to B is not there in the relation. Here it is not there. Okay, is it there? No. So 1 to B is not there, therefore we kept it as 0. Similarly, 2 to 1. Is there any 2 to A? No. 2 to A? No. So it is 0. Okay, 2 to B. Yes, it is exist in the relation 2 to B. Therefore, we kept it as 1. Okay, 3 to A. 3 to A is there? Yes, there. Therefore, we kept it as 1. 3 to B. Is there any 3 to B here? No. Therefore, 0. So, it is the way of representing the relation in matrix form. So, if the number of elements represents rows of the relation matrix, and the number of columns represent the number of elements in the set B represents the columns of the relation matrix. So how many number of rows here? 3 rows and 2 columns. 3 by 2 matrix. It can be represented as 3 by 2 matrix. Clear? It is the representation of the relation in matrix form, or matrix representation of a relation. Clear? Now coming to digraph representation of a relation. What is the digraph representation? Digraph representation is nothing but we need to take the elements 1, 2, 3. Say for example, A is equal 1, 2, 3, B is equal A comma B. Here the relation is 1 comma A, 2 comma B, 3 comma A. Now we need to take these elements as like this: 1, 2, 3. You can take this in any where, above or below, doesn't matter, and the set B elements are A comma B. Now we need to observe, is there any relation from 1 to the elements in set B, the set A elements to set B elements. So yes, 1 comma A is there in the relation. 1 comma A is there. 1 comma A, right? Where it is, my sticker. Right. 1 comma A. Yes. Okay. 1 comma A there. Therefore, we need to keep, like this. We need to represent like this, and arrow should be to A. And is there 2 comma B? Yes, 2 comma B is also there. So 2 comma B, arrow should be like this. 3 comma A is there? Yes, 3 comma A is also there. So we need to like this. So in this way we can represent a relation in digraph form, right? It is the digraph form of the matrix. Now types of relations. So first one is reflexive relation. Reflexive relation. So what is reflexive relation? A relation R on a set A is reflexive. A relation R yes, I didn't get a relation. Okay. A relation R on a set A reflexive. A is reflexive. Right. Now we see a relation R on a set A is reflexive if A comma A belongs to R for all A belongs to A. A comma A belongs to R for all A comma A. That means the relation from the element to itself. A comma A belongs to R for all A belongs to A. So if we take any relation A 1 comma 2 comma 3, then R is equal to 1 comma 1, 2 comma 2, 3 comma 3. So it is clearly a reflexive relation. That means for all the elements, the self relation exists. 1, 1, 2, 2, 3, 3. For example, if 2, 2 is missed here, then it is not the reflexive relation. Okay. If any of these three values missed, any one of the three values is missed, then it is not the reflexive relation. Okay. So we'll see next relation. Irreflexive relation. A relation R on a set A is irreflexive if A comma A does not belongs to R. A comma A does not belongs to R. For all A belongs to A. Okay. So like the previous relation, we take A 1 comma 2 comma 3, then 1 comma 2 2 comma 3. That means 1 comma 1 does not exist in this relation. 2 comma 2 is also does not exist. 3 comma 3 is also does not exist. Therefore it is irreflexive relation. Okay. A relation R on a set capital A is irreflexive if A comma A does not belongs to R for all A belongs to A. And if every A comma A should not be there in the relation, then it is said to be the irreflexive relation. Now non-reflexive or not reflexive. Non-reflexive means for some values of A it may exist and for other values it may not exist. That means self relation does not exist. Then that is said to be non-reflexive relation. So here 1 comma 1 is there, but for 2 comma 2 is not there, 3 comma 3 is not. That means it is not the completely reflexive relation. It is partially reflexive relation. That means it is non-reflexive relation. Non-reflexive relation. It is not irreflexive. It is non-reflexive relation. Clear? Now coming to the symmetric relation. What is symmetric relation? If A comma B belongs to R implies that B comma A belongs to R. That means if at all A comma B is there in the relation, then it should be B comma A also belongs to the relation. Clear? Therefore, we take one example. Say A equals 1 comma 2 comma 3. 1 comma 2 is there in the relation. Therefore, 2 comma 1 should also be there. If 2 comma 1 is not there, then it is not the symmetric relation, right? So if 1 comma 2 is there, say if 1 comma 3 is there, then 3 comma 1 should be there. 1 comma 4 is there, like that, right? So 1 comma 2 is there, 2 comma 1 is also there, then therefore it is symmetric relation. Asymmetric. A relation R is asymmetric if A comma belongs to R implies B comma A does not belongs to R. Okay, did you get the point? A comma B belongs to R, then B comma A should not be there, then only it is said to be asymmetric. So R is equal to 1 comma 2 is a relation, but 2 comma 1 does not belongs to R. So if 1 comma 2 is there, 2 comma 1 is also there, then it is called symmetric relation. If 1 comma 2 is there, 2 comma 1 is not there, then it is said to be asymmetric relation. Asymmetric relation. Clear? Now antisymmetric relation. What is antisymmetric relation? Relation R is antisymmetric if A comma B belongs to R and B comma A belongs to R implies A equals to B. Okay. So R is equals to 1 comma 1, 2 comma 2. So A comma B is there and B comma A is there, then it is said to be antisymmetric relation. Clear? 1 comma 1, 2 comma 2, 1 comma 2 is there, but 2 comma 1 is not there. Okay, did you get this point? So if 1 comma 2 is there, then 2 comma 1 is also there, then it is not anti-symmetric relation. It is said to be symmetric relation. Okay, so 1 comma 1 is there, 2 comma 2 is there, 1 comma 2 is there. So it is not symmetric relation. It is anti-symmetric relation. If 1 comma 2 is there, 2 comma 1 is also there along with 1 comma 1, 2 comma 2, then it is symmetric relation. It is not the anti-symmetric relation. Okay, so whenever it is anti-symmetric, then it is not symmetric. If it is symmetric, then it is not the anti-symmetric. Clear? Transitive relation. Okay, So transitive relation means a relation R is transitive if A comma B belongs to R, B comma C belongs to R, implies A comma C belongs to R. So A comma B belongs to R, B comma C is also belongs to R, then it should be A comma C belongs to R. If these two exist, A comma B as well as B comma C exist in the relation, then A comma C must also exist in the relation. This is called transitive relation. This is called transitive relation. Say for example 1 comma 2 exists, 2 comma 3 is also exist. Therefore 1 comma 3 should be exist. Yes, exist. Therefore it is transitive relation. Clear? So 1 comma 2, 2 comma 3. What is common element here? 2 is the common element. So 2 is the common element. So 1 comma 2. So sometime I am not getting this. So I will indicate with only indicator. Right. Okay. Okay, na? Example. So 1 comma 2, 1 comma 2 is there, 2 comma 3 is there, and 1 comma 3 is there. So it is called transitive relation. Now non-transitive relation. Non-transitive 1 comma 2 is there, 2 comma 3 is there, but 1 comma 3 is not there. It is said to be the non-transitive relation. Clear? So these are the types of relations. Now one more most important relation is equivalence relation. Equivalence relation. When we say that a relation is equivalence, when we say a relation is equivalence, a relation that is reflexive, symmetric and transitive, then that relation is said to be equivalence relation. The relation should be reflexive, symmetric and transitive, then the relation is said to be equivalence relation. So for the set A is equals to 1 comma 2 comma 3, if we write the relation 1 comma 1, 2 comma 2, 3 comma 3, 1 comma 2, 2 comma 1, 2 comma 3, 3 comma 2, 1 comma 3, 3 comma 1, it is, yes, equivalence relation, because for all the elements the self elements are exist. 1 for 1, 1 comma 1 exist, for 2, 2 comma 2 exist, for 3, 3 comma 3 exist, and 1 comma 2 is there, 2 comma 1 is also there, 1 comma 2 is there, 2 comma 1 is there, therefore 1 comma 1 is there, yes, and 2 comma 3 is there, 3 comma 2 is there, therefore 2 comma 2 is there. Clear? So 2 comma, and 1 comma 3 is there, 3 comma 1 is there, therefore 3 comma 3 is there, right? So this is the symmetric relation. And one transitive means 1 comma 2 is there, 2 comma 1 is there, 1 comma 1 is there, right? So transitive relation. Okay, so it's satisfying all the three properties, therefore it is said to be equivalence relation, right? Next, the relation satisfies reflexivity. A comma A belongs to R, symmetry, A comma B belongs to R, B comma is also belongs to R, transitivity, A comma belongs to R and B comma C belongs to R, then A comma C belongs to R. Now we will see one most important example for the equivalence relation. Very important. It was asked a number of times in your NSM examinations. Congruence modulo M is an equivalence relation. Congruence modulo M is an equivalence relation. First of all, what is congruence modulo? The relation congruence modulo M on integers is defined as A congruence modulo to B. A is equivalence to B mod M. A is equivalent to B mod M is said to be the congruence modulo M. A is congruent modulo M. If and only if, so what is the meaning of this? A is equivalent to B mod M means that if and only if A minus B is divisible by M. A minus B, if A minus B is divisible by M, we say that A is congruent modulo to M. So for example, if I take M is equals to 3 here, So if I take m is equal to 3, 0 comma 0 is divided by 3, and 1 minus 1 is also 0 divided by 3, 2 minus 2 is also 0 divided by 3, 3 minus 3 divided by 3, 4 minus 4 divided by 3, 0 minus 3, 0 minus 3 minus 3 divided by 3, 3 0. All these elements are divided by 3. Therefore, this is a equivalence relation. The relation is reflexive, symmetric, and transitive. If we observe these elements 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. So if I take 1 comma 2 comma 3, therefore it is a congruence modulo relation. Clear? So this is the types of relations and equivalence relations and relations. Thank you very much for listening the class. We'll see one more class soon. Thank you.